Okay, questions from Lab 12A. I'm assuming at least one person's going to want follow-up number 1, if nothing else. That's dead. Are you dead? Other than follow-up number 1, is there anything else? Number 1, number 2. All the follow-ups? No, that is all the follow-ups. Yes. Analysis 8. Yep. Analysis number 8. Yes. Analysis 3 and 6. Anything else? Yes. Number 5. Okay. All right, so let us start with the analysis. We'll just kind of go in order of the lab. So analysis number 3, it says if the hydrated cobalt-2 ion complex were refrigerated, and that would be this equilibrium where we have CO, H2O, 6, 2 plus, and this is red, plus 4, Cl minus, in equilibrium with CO, Cl4, 2 minus, aqueous plus 6, H2O liquid, and this one is blue. All right, so when you heated the cobalt complex, what happened? Yes. It turned purple-blue, yes. What happened when you cooled it? It turned pink, red. So what would you expect to happen if you refrigerated it? Red. Boom, done. Were we overthinking that one? Yeah. Okay, seriously, that's all there is to it. When we cooled it, it turned red. So if I put it in the refrigerator, it would turn red. Yeah. Okay, number 5. Predict how the addition of sodium chloride would affect this equilibrium. And so again, we're looking at this one. So now we're doing analysis number 5. And now we are adding NaCl. What are we really adding if we're adding NaCl? NaCl, what does it do in solution? It dissolves and dissociates into what? Na plus and Cl minus. So out of those 2 ions, which of those will have an effect on the equilibrium here. The Cl minus, okay, so it's the Cl minus. So what have we done to the concentration of Cl minus? We added NaCl, so the concentration of Cl goes up. So we have increased concentration of Cl minus. So which way will this equilibrium shift? Equilibrium shifts right. Therefore, it turns blue. Is good? You okay, Lauren? You got a question? What if it shifts right, it's going to turn blue. So for analysis number 3, it turned red or pink, but now we're on analysis number 5. I'm just using the same equation here. So if we add the sodium chloride, that's for number 5, then we increase the concentration of chloride, it shifts to the right and it turns blue or purple. You could say either. Okay, let's see. So that was number 3, number 5. We also wanted, I think, number 8, but let's just check. 6 and 8. Did I move that too fast? There we go. 6 and 8. Number 6, write the balanced equation for the reaction of Cr2O7 2- with OH-. We did this last day. I gave you a handout with it in it. Didn't we? We've done this one. It's in your handout. Shall we do it again? What the heck? Why not? Okay, let's do it again. Okay, number 6. So we're going to start with Cr O4 2-. This is the reaction given on page 163 or 167. 167. We have 2 of them, plus 2H plus, in equilibrium with Cr2O7 2- plus H2O liquid. All right. So we want the reaction of Cr2O7 2- with OH-. So what do we want Cr2O7 to be, a product or a reactant? We want it to be a reactant. What could we do with this equation that we have right here in order to make Cr2O7 2- a reactant? We could just reverse it, okay? So we're going to reverse it. So let's do that. We have Cr2O7 2- plus H2O in equilibrium with Cr O4 2- plus 2H plus. All right. Now, we want this thing to be reacting with hydroxide, but in our equation, we have hydrogen ion. How could we turn this thing from being acidic to being basic? We could add what? We could add OH, yes. To neutralize the H plus. So how many OHs will we be adding? We'll be adding 2. Now, remember my original equation, oh, and I forgot 2 here. Okay, we need that too. My original equation was balanced, yes? I have now added 2 hydroxides to the product side. Is this equation still balanced? No. Are we remembering me doing this another time? Yeah, this is ringing bells, right? So what are we going to have to do in order to keep that reaction balanced? That will not work, because then you'll end up with more hydrogens. We're going to add 2 OH to the reactant side as well. What we do to one side, we do to the other side, okay? And then we add it up. Our reactants are, we've got Cr 2O7, 2 minus, plus H2O, plus, and our third reactant now is 2OH minus, in equilibrium with 2 CrO4, 2 minus, plus. Now what do we get when we put 2 H pluses together with 2 OH minuses? We get 2 H2Os. Is there anything else we should be doing with this equation before we say we're done? Pardon me? Yeah, we can cancel out one of the H2Os because I've got H2O on both sides of the equation. I don't really ever want to have chemicals on both sides because, you know, that doesn't really, that's not how we write equations. So I can cancel that out and that will leave me with 1 H2O. Anything else missing from here? States, aqueous, all our ions are aqueous, aqueous, and water is liquid, and we're done. Woo! Analysis number 8. Compare the relative solubilities of barium chromate and barium dichromate. Well, on page 167, we are told that Ba2 plus ions react with CrO4 2 minus ions to give solid BaCrO4. And then it shows us the reaction Ba plus CrO4 2 minus in equilibrium with BaCrO4 solid. What does that tell you about the solubility of barium chromate? It has low solubility because when I mix those two ions together, aqueous ions together, we get a solid, okay? I don't know why together is two words there, but that's okay. Get a solid. Now, because it has asked us to compare the relative solubilities, if BaCrO4 is low solubility, what does that imply that barium dichromate is? It's soluble, yeah, okay? Okie dokie. Follow-up number 1. I'll give you a minute to finish writing there. Omar, Amina, do you guys have a question? You're okay? Okay, cool. Yeah, I just want to make sure it wasn't confusing for you there. Okay, follow-up number 1. There's no good way to abbreviate follow-up. Just let me know. Yeah. No good way, no. When silver ions are added to the red FeSCN2+ ion in part 2, the color disappears. So what it is saying is that in our equilibrium is as follows. We have the Fe3+ ion, which is yellow. We have the SCN- ion, which is colorless. And we have the FeSCN2+, which is red. So I now have a beaker that contains Fe3+, SCN-, and FeSCN. And I could draw more of them, but I'm only going to draw one because it just makes my life a little bit easier, yes? Okay, and this one is red, so the solution appears what color? Well, orange or red, you know, red/orange, okay? So we got that. Now what we're told is that we add to that Ag+ ions. And it says the color disappears. The red color disappears. What must have happened to our equilibrium? It must have shifted left. We are also told that a white precipitate of silver thiocyanate appears. Are you guys okay with the concept that a precipitate is a solid? Okay. We are going to be going over that, but we will be using that term a lot in this unit. So a precipitate is a solid that forms when you mix a couple of solutions. So what has happened is we add in the Ag, and now in our beaker, instead of having the red FeSCN, the Ag got together, the Ag got together with the SCN and formed a solid. Yes? That caused our equilibrium to shift to the left. So we have our original Fe3+. The SCN is now it's now gone because it has reacted with the Ag+. And the FeSCN separates into Fe3+ plus SCN minus. Yes? And you see the red stuff is gone. We have a white precipitate. Who does silver prefer to be with? Or sorry, who does SCN, not silver, who does SCN prefer to be with? Fe3+ or Ag+? Yeah, it prefers to be with the Ag because the Ag was successful in displacing the iron. The iron was with the SCN, and now the silver is with the SCN. Yes? And so this is where we get to when it asks us why Fe3+ can be used as an indicator. What is an indicator? Yeah, it shows us that a reaction is complete. Do you remember when you did the titration? Did you add an indicator? Yes. So every time you added some sodium hydroxide, it would react with the hydrogen that was there. Yes. But the solution didn't turn pink until all the hydrogen was used up. Yes? So an indicator is a substance that turns color when a reaction is complete. Therefore, what if we were to set up a titration What kind of equipment do we need for a titration? Tell your partner. I'm going to get super lazy. I'm not going to show the ring clamp and everything because that's just going to get messy, right? What is this thing called? That's a burette. And in our burette, we are going to put an SCN minus solution. The question, follow-up number 2, asks, how can we use Fe3+ as an indicator to find, sorry? Oh, number 1, yes, you're right. As an indicator to find the concentration of Ag+ in a solution. So we're going to have a solution that contains some concentration of Ag+. Yes? What do we put underneath the burette? A beaker. Is this what you did? Is that what it looked like? Was that your setup? Oh, yeah, it was a what? An Erlenmeyer flask, yes. Okay. So we have an Erlenmeyer flask, and in our Erlenmeyer flask, we have a solution, and we are going to have 1, 2, 3 silvers in there. And we're going to pretend that we don't know that. Okay, so it's going to be a mystery to us how many silvers we add. And we are also going to have an iron 3+, and that's going to be our indicator. Yes? So if we have 1 drop of SCN-, let's just say it contains a single SCN- ion, what happens in our beaker? Or in the flask, rather. SCN- is now going to go in there. What's it going to do? I want to know what it's going to react with. Is it going to react with the Ag or with the iron? The Ag, why? It prefers it over the iron. Remember, because the silver managed to displace the iron? So, SCN- reacts with Ag+, which it prefers over the iron. What does that reaction look like? It looks like this: Ag+ plus SCN- goes to AgSCN. What state is the silver thiocyanate? It is a solid. What kind of a reaction is this reaction? I'm looking for something, not one of the sort of 6 major types. I'm looking for something that starts with a P. Precipitation. Okay, so we added one drop and we got AgSCN gives AgSCN. So what happens to that silver? It is now gone. Okay. Add a second drop of SCN minus. What happens? React with another Ag. We get Ag plus SCN minus goes to AgSCN solid. That's aqueous. That's aqueous. And that means that, boom, another one is gone. Yes? Third drop. I don't know what's wrong with my pen. It just went crazy. I got 7 3s all over top of each other. Add a third drop. Aren't you glad I only drew 3 silvers? What happens? It reacts with another Ag. Okay? Ag plus SCN, woo! CN minus goes to AgSCN solid. Okay? So the solution is getting, what would it look like if we've got a white precipitate forming in it? It looks cloudier. So it gets cloudy, but how are you going to tell when it stops getting more cloudy? Because I could add another drop, yes, and if I didn't have the iron in there, it would just look kind of cloudy still, Faith. You guys hear that? Once all the silver is gone, the next drop of SCN has no choice to react with the iron, which produces a red color, which tells you that the reaction is finished. Yes? The appearance of the red color indicates that the reaction is complete. Is good? Okay. Follow-up number 2. A student discovers that after doing part 4 of the experiment, several of the test tubes are coated with a yellow precipitate that does not wash off easily. Devise a chemical method for removing this material. What is that yellow solid? It is a precipitate. Yes, it is. And if you go look on page 167 in your lab book, you will see that we have follow-up number 2. This particular reaction, Ba2 plus CrO4 2 minus in equilibrium with Ba CrO4 solid, and that is a yellow precipitate. PPT is the abbreviation for precipitate. If we want to get rid of the solid, what do we need to do to this equilibrium? Yeah, we want to shift it left, away from the solid. Whoops. How are we going to do that? We can decrease the concentration of the reactants. Because equilibrium always shifts towards a decrease, yes? All right. Now, I'm going to write the other reaction that is relevant, that is on page 167, and that is the following. 2CrO4, 2 minus plus 2H plus in equilibrium with Cr2O7, 2 minus plus H2O liquid. How could we use this equilibrium to decrease the concentration Oh, don't do that. There. Okay, so we're going to pick on CrO4 2 minus because it's present in both of these equilibria. These will both be happening in the same container. If you have chromate, it will do both of these things. Yes? What would we want to happen to this equilibrium to decrease the concentration of chromate? Chat amongst yourselves. I'm going to give you guys some choices here. You keep talking amongst yourselves and you can decide what you think. Yes, of course. Would adding chromate have the effect of decreasing the concentration of chromate? No, that would be silly. Well, and we can't really say decrease the concentration of chromate because that's what we're trying to get this equilibrium to do in the first place. So that's also not an option. How about increasing the concentration of hydrogen? Will that work? Yes. Obviously, that means that decreasing the concentration of hydrogen will not work. Would it work if we increased concentration of dichromate? No, because that would shift it to the left, which would mean that we would have more chromate, right? How about decreasing the concentration of dichromate? Yes. So either of these are good options, but this one is much easier to achieve, okay? Because I would have to go and figure out something that will react with the dichromate, that won't react with the chromate, and it gets really confusing really fast, yes? So this is okay but complicated. And you might end up with another precipitate on the wall of your thing, which would not solve your problem, right? So adding hydrogen is going to be your best option. So I'm going to get rid of that one. How are you going to get hydrogen ions? Yeah. What can you use to get H plus ions? You can use HCl. Okay? So if you add HCl, that increases the concentration here, which shifts this equilibrium to the right. Therefore, the concentration of CrO4 2- decreases. Therefore, the first equilibrium the concentration of CrO4 2- decreases, which means that it will shift to the left away from the solid. Okie dokie dokie. So, you feel okay about the lab? We'll be able to finish it tonight. Get handed in tomorrow. Pardon me? Most likely. Okay. What we're going to do right now is we are going to take a look at Unit 3. And you guys did 3.1a. Are you feeling good about molecular and ionic compounds? Yes? Okay. We are going to take a look at 3.1b. Yes. Yes, you need to fill out all the stresses and shifts in your tables in the lab. Yes. Fill in all the stresses and shifts in the tables in the lab. Okie doke. All right. Omar, remind me, when are you writing your test? Didn't we set something up? Do you have a spare? No, you don't have a spare. So you were supposed to write it today during class. Can you come after school today? Yeah? Okay, cool, let's do that. All right. So we want, what am I doing now? Right, we're going solubility. Come on, there we go. 3.1b, ionic and molecular compounds. So you can recognize and make sure that you read these boxes as you go through. Read the boxes. Recognizing ionic and molecular compounds. Ionic compounds begin with a metal or with NH4. Anything else is molecular. Yes? We're not going to take time to do the exercise right now. We're just going to go through the rules to make sure that you feel okay about them. So those are your ionic compounds. Acids. Acids either begin with an H or they end in COOH. Okay, so you are then going to go back to question number 1 and circle all the ones which are acids. Okay? Writing dissociation equations for ionic compounds and acids. To dissociate means to take apart, and so you're going to separate the cation and the anion. And we've been practicing writing dissociations for the last week, so hopefully these won't be too bad. Don't forget to include your states, the charges, and make sure everything is balanced. There is one that's a little bit tricky, and that is if you have a COOH acid, and it is the hydrogen at the end that comes off. Okay? So all the front part will be the anion, and then that H at the end comes off, if it's a COOH acid. So if we look at just a few examples here, we've got some pretty straightforward ones. NaCl, there's one Na, one Na, one Cl, one Cl, that's pretty straightforward. The only thing to bear in mind is if you have a little 2 down here, where does that 2 have to go in the dissociated part? It has to become a coefficient, because that means those Fe's are floating around separately from one another. Okay? And similarly, if we have our little 3 down here, that becomes a 3 in the front. Okay? And don't forget, acids come apart, right? We get our H plus and our H plus. And if you have a COOH acid, what comes off? The H at the end. Okay, so you're going to be able to write dissociations for those. Now, whether you call this dispersal or whether you just call it dissolving, do you remember from those Tyler videos, what happened when you dissolve sugar in water? Does it dissociate? No, what happens to it? The molecules just separate from the other molecules. Basically, we're breaking intermolecular forces and we're putting the waters going in between. So you don't have to write anything any different at all. So if we have CH3F and it's a gas and I bubble it into water, the only thing that changes is the state. So it goes from being gas to being aqueous. The sugar went from being solid to being aqueous. So the only tricky part is to recognize that about the compounds. So it's a molecular compound if it does not start with metal or NH4 and it is not an acid, okay? So there you're going to practice writing dispersal equations. Electrolytes and non-electrolytes. Do we remember what an electrolyte is? Electrolytes, what do they conduct? They conduct electricity. What do you need to conduct electricity? You need ions. So what kind of solutions will conduct electricity? Solutions of what kinds of compounds will conduct electricity? Ionic solutions, also solutions of acids, okay? So soluble ionic compounds and acids are electrolytes. But if you have those molecular compounds that are not acids, those are non-electrolytes and they will not conduct electricity. And then there's just a little picture here showing you the difference. Here we've got charged particles that can move. And over here we have no charged particles. If you don't have charged particles, you cannot conduct electricity. So what's that word that we use for that solution that contains the dissolved ions? It's called an electrolyte. So think about it this way. If you ever drink something like a sports drink, right, that contains an electrolyte, does it taste just a tiny bit salty? Yes, and that's because you have dissolved ionic compounds in there, usually some sodium chloride, maybe some potassium salts in there, okay? Electrolyte, just like in Gatorade. Yep. Okay, you have dissolved salts. Or acids. And that's why they taste a little bit salty. So if you know electrolyte from that context, you can be like, oh, now I can help. That sort of helps me remember the word electrolyte, right? Because I know that's where it comes from. And then sugar would be a what? Non-electrolyte. Okay. And if we look on our next page, we've got, you can actually see the particles move. If we have our battery here, and if this is the negative terminal of the battery, and this is the positive terminal of the battery, you can see that the positive sodium ions, where are they moving? Towards the negative, and the negative ions are moving towards the positive. And the sugar just sits there and does nothing because it has no charge, so it's not attracted to the positive and negative. So you can then do these questions on electrolytes, and then we're on to the answers. So how about you guys take the rest of class to kind of work on that? Yeah? And if you've already finished that and you want the next thing, I can give you the next thing. I have it ready, but you don't have to take it today. And if you want it today, you can.
So folks, I'm gonna be here after school today. So if you want to come by and like ask questions on your lab, that's cool. If you just want to stay to me and get it done, wouldn't be worst use of your time.